Hello there, welcome back to yet another research paper walkthrough video, where this time we'll be going through this one of the most cited recent works in the pruning and building efficient neural network space. The paper is titled as Learning Both Weights and Connections for Efficient Neural Networks, and it's from researchers from Stanford University and NVIDIA. But before moving forward, if you're coming across to this channel for the first time, my name is Prakhar Mishra, and on this channel I create content around ML NLP where I explain papers, quick graspable concepts in the form of shorts and much more. So if that excites you, then don't forget to hit the subscribe button and I guarantee that you'll not regret. Also, I have a free email monthly subscription which will shoot an email on the 3rd of every month regarding all the videos that have been released in the previous month on this channel. So if you're interested in availing that service as well, there's a link in the description below. Make sure to fill that Google form and you're good to go. So with that said, let's start with the paper. So at very high level, the paper proposes a 3-step method that helps in reducing computationally expensive and heavy neural networks to a performant one with almost no drop in the accuracy numbers. While experimenting, they show that the AlexNet and VGG16 on the ImageNet datasets can be pruned to somewhere close to 9x to 13x of their original size, still giving almost equivalent accuracy numbers on the test set. And clearly, if you're not dropping on the accuracy numbers and you're able to build networks that are almost 9x to 13x smaller than the actual ones, then these models make up a good candidate for on-device deployment as well. So that's the major theme of the paper, where they introduce this 3-step method. So let's move forward and see what these 3 steps constitute of. So this is how the training pipeline looks like. So you start by training a neural network, typically the way you would do. And once this training is done, you prune the connections that have low weights, or in other words, at least the network considers those weights to be not important during the training phase. And once the pruning of those weights is done, you'll have a less dense and relatively smaller network, which you again fine-tune for the remaining weights. And you keep repeating this process iteratively till a certain threshold of the performance. So yeah, that's the entire idea. So let's say this is the first step. This is before pruning and this was the network that you were to train. Once the training is done, you remove the unimportant ones. So this is the relatively sparser version of the same network, where you would remove the edges that had low weights, and you could do it based on certain threshold. And eventually you'll also remove the nodes if there are no in nodes or no out nodes after the pruning of these connections is done. So that way you're removing both synapses, which is the connections, as well as the neurons. So let's say this is one of the states that you get after first level of pruning. Once this is done, you again train the model with this network for the remaining connections that you had, and you could again go around in the loop as we discussed earlier in this figure. So yeah, that's the entire idea, and that's what they have written, which is that unlike the conventional training, we are not learning the final values of the weight, but rather learning the connections which are important. So that's what you do with the first level of training before you prune those weights. Post second step onwards, you remove the low weight connections, and hence converting your dense network into a sparse one. You again train this network for the final weights of the remaining sparse connection. You keep doing this iteration till you have a pretty sparse and small network with very less impact in the actual accuracy. So if you see the intuition behind this approach, in any neural network or any sort of machine learning system, clearly all of the weights won't be equally important in determining, let's say, if it's a cat or a dog. So that's what the researchers bang on and say, let's do one level of iteration and see what all weights are important in the first place. So the first step, once they find, okay, these are the weights that are important and these can be removed because the relative weights that are given to these weights is very small. So once this pruning is done, the first benefit that you find is clearly you have a smaller and a sparse network, which is now efficient in terms of its storage. The best thing is that you are still able to retain almost equivalent accuracy because you have removed non-important nodes, or in other words, not so contributive nodes that were present in the original network. So once that is done, let's say these were the 4 nodes that were left and these were the connections that were left, and this is the task that you have to do. Now you have some predetermined weight values already for these winning or important edges. But again, if you see, right, these weights were relative to the original connections that you had. But now since you have removed the original connections, it's better to again readjust these weights with the initializations that we have, because this is acting as a prior stabilized weights. Now once the second level of training is done with these prune weights, you will again see the distribution of weights across these edges, where some of them are really high and some of them are really low. So depending on at every step, the way you calculate your accuracy and you see a deviation happening downwards, you can stop at that point. Because again, the priorities could be different. You might want to deploy this on a mobile device, let's say, where a drop of 3% accuracy is still fine with you. Because if you see, right, an end user would not notice a 1% to 2% drop in the accuracy numbers. Rather, if this drop leads you to, let's say, 8x smaller model size, which is fast enough and can be stored and can be run on device, that's always a better choice to hold on. So yeah, that all depends on what use case you're trying to solve. You would want to iterate this pruning and retraining step those number of times. So yeah, that was the main idea, where at every step you just keep in the winning edges, which are most contributive, and keep removing the ones that don't contribute much. Also, just to note a point, fine tuning that you do with the sparse network is done based on the weights that you get from the pre-trained network. You need not start by randomly assigning these weights again and start the process from scratch. Because the pre-training has already given you some local minima, you should always use those weights to reach to a better local minima. So yeah, that's the idea. Authors, apart from this, play around and see the dropout ratio adjustment, like what should be the dropout ratio post fine-tuning and after fine-tuning, where the idea of dropout is to essentially probabilistically drop either connections or nodes during the training phase, which eventually allows for all the nodes to learn some generic pattern rather being dependent on some of the nodes for making the final decision, which is called as overfitting. So in the pruning scenario, the authors say that the dropout ratio for the fine-tuning stage, which is again when you retrain after pruning those weights, should be lower than what you had earlier. Because now after the first level of iteration, let's say if you have come from 10 nodes to 8 nodes, you have already reduced the model capacity. Now if you still have a higher dropout ratio under this condition, you might not have enough neurons to learn the pattern that lies in the data, and which will eventually lead to underfitting. So the dropout ratio can be higher in this front compared to what you have in fine-tuning stage. So that's what this equation says. DR is the dropout ratio in the retraining phase, and this is the original dropout ratio. CIR is nothing but the number of connections in layer I during retraining and the number of connections in layer I in the original case. So once the pruning is done, CIR is supposed to be less than CIO. So eventually you multiply DO with something less than 1, which gives you DR, which is less than DO. So yeah, that's how you can mathematically define the value of DR. Also, one more thing, at first it might look like the dropout and the pruning are more or less the same thing what we're trying to do, but there is a small difference, as in for example, let's say in dropout, the dropping of the parameters or neurons is done only in the training stage, and during inference all the weights are activated. Whereas in this pruning scenario, during training, as soon as you remove certain number of weights, those are never ever available to the model again. So that way pruning leads to permanent drop off in the weights, which is unlike the case in dropout. Okay, moving forward. So yeah, we have seen about iterative pruning, like you have to do it n number of times to get to the ratio which is close to 5x to 9x. And then again, if the weights coming to a neuron were pruned or maybe going outside were pruned, then you can easily remove this node as well. I think now we're done with the paper. So that was the entire idea of the paper essentially. Then they have results and experiments. Cool. So yeah, that was it for the paper. If you like such content, make sure to hit that like button and subscribe to the channel. Also share it across your friends to whosoever is interested in such content. I'll meet you in the next one. Bye bye and take care.